Hello, welcome to the latest video from iLearn Engineering. Today I'm going to be looking at how to calculate the shear force and bending moment diagram for a simple cantilevered beam with a single discrete load on it. Alright, well first of all, before we go in and do the calculations, let's just have a look at some examples of a cantilevered beams in action. Well, my classic example of this is obviously an aircraft wing, but even in civil engineering you will find cantilevered beams. So, in order to understand what's going on inside the structure, we can look at internal loads. And these are often referred to as shear force diagrams or bending moment diagrams or torque diagrams, number of different terms, but they're all looking at the same thing. They want to try and understand how the load changes as you move along the structure, inside the structure. And to do that, we take some imaginary cuts and we apply equilibrium, and I'm going to show you with an example what I mean by that. So I've got on the screen here my cantilevered beam, and I am going to apply a single or a discrete load, and I'm going to call that P. That P represents the force applied to the beam. And I am going to define some dimensions on here, so I'm going to refer to this section here as being distance A, and I'll refer to this distance here as B. And I'm going to show you that I'm going to take some cuts. I'm going to define one here. So this will be position 1 if you like. And then position 2 is anywhere between the root of the beam and the applied load. So that's number 2. Position 1 and position 2. Okay, and finally I want to define a coordinate system. I'm going to start from the right hand edge, working left, and I'll call that X in this example. So let's look at the first cut. So the first cut is at position 1, and we have a little section of a beam there, and when you take your cut, you have to still apply equilibrium. So what forces are inside that beam in order to maintain the equilibrium of the beam? So if I take a cut and the beam does not fall down, then there must be an internal vertical force, which we call, or often use the letter Q for, and then going to be a bending moment at the cut to prevent any moments bending, and so I'm going to call that M for moment. So that's the moment about the position of the cut. And then I'm going to look at applying equilibrium. Now, if we just take a step back here away from the problem and think in general, recalling Newton's laws, we said that the sum of the forces in any particular direction, for instance x, is equal to the mass times the acceleration in that particular direction, x in this case. And there is no acceleration in our problem. It's not a dynamics problem, it's a statics problem, so this acceleration term is 0, and so therefore the sum of the forces in any particular direction must be 0. Okay, so we can use that principle when we look at this small section where we make the cut, and we can say, well, if we resolve the forces in the vertical direction, taking up as being positive, then we would look at, we've got a Q there, there's no other forces, and that must equal 0. Similarly for the moment, if we take moments about the cut, that's what we're doing there, anti-clockwise being positive, then the moment again is equal to 0. There's nothing on there, there's no shear force and there's no bending moments at the end of the beam, all the way up to the force here, really, because things are going to change there. And in order to look at when the how the conditions inside the beam change at the position of the force, that's where we've got to look at cut number 2. So let's do cut number 2, and so I'm going to draw here a sketch of the beam, a bit wiggly, there you go. Let's move it down a bit now. And so we have got the position as being X. Don't forget we've got an applied load somewhere there. So that's P. There it is. And P is at position A from the tip of the beam. And in order to maintain equilibrium, we have to have these internal loads. So we've got a Q at position X, and we've got a moment at position X. So this is cut 2. Let's just label this one. So this is cut 1, and this is cut number 2. Now let's apply the rules of equilibrium on the right hand side here. So resolving forces as being positive vertical. Let's start. So we start from the left hand side. What have we got? We've got force Q being vertically up as being positive, and then as we move going towards the right of the beam, going left to right, we find the green force P, but it's acting down, so it's going to be minus P. And don't forget that the Newton's law said that if we sum up all the forces in a particular direction, they have to equal to 0. Well, we've done that. This is summing up the forces here. This bit here, that is us summing up the forces in the X direction, and then they have to be equal to 0. Okay. Similarly, with the bending moments, if we take that way anti-clockwise as being positive, then we'll start with the actual cut moment, which is M, that's the internal moment, and then we walk towards, move left to right, then we come across a force P, and that force P has got a perpendicular distance to the cut, so that's going to produce a moment, turning moment. Let me do that in a different colour here. So the distance here from the cut to where the force is, that is going to produce, when the force P is multiplied by that perpendicular distance, that will give us a moment. So that distance there, it's just sort of this distance here, that's X minus A. That's what that distance is. So the moment is going to be, well, it's going to be opposite direction. It's going to be minus, and then it's going to be P multiplied by the moment arm, if you like, which is X minus A. Well, this bit here is us summing up, or we're summing up the moments this time. This is summing up the moments about the cut, and they have to equal 0 in order to maintain equilibrium. So we have our two equations there which show us how the shear force and bending moments are distributed along the beam. So we're now going to come down and I'm going to draw some shear force and bending moment diagrams for you. So we'll scroll back up again so we can remind ourselves we've got the beam there cut at position 1 and 2. And then we are going to draw our shear force diagrams now. So I'm going to do a sketch. So here I've got Q, this is going to be Q, and I've got a distance along the beam. Okay, and then I'm going to define this moment, this point here. It's going to be the end of the beam, if you like. So there I've got position A, and then B sort of down here. Okay, so this is sort of, that represents A, and this represents the distance B. Okay, so we knew anyway, we knew if we go back, scroll back up, we can see here, let's have a look, the shear force is 0, and the bending moments were 0 everywhere at the first cut. So if we the first cut here, we have a 0 shear force, and then when we come up here, What does the shear force equal on the second one? Well, we didn't rearrange the equations, did we? We can do that now. Let's rearrange the equations. So with the first one, this one here, well, we can just say that Q equals P. It's very straightforward. And with the second one here, just take everything to the side, so the moment, take the whole bracket to the side, equals P to X minus A. Okay. So those are our two equations. I can highlight those if you like. Oops, let's highlight those. There we go. So those are the ones that we want to now plot on this side of the beam. So let's get my blue pen out. So we're going to change, it's going to be a step up here. And then the shear force just has this constant value of P. Okay, whatever that is in newtons. And then if we come down, we do the same for the bending moment now. Let's draw or sketch the units here. So we've got A there. So we know that the bending moment was 0 at the first section of the beam. So same again, we've got 0 bending moments. Then what happens, well, we look at the nature of this equation, the moment equals P into X minus A. So that's a linear equation, the equation of a straight line. Now, if we set the value of X, because X is the variable, so if we set the value of X to the full length of the beam, we'll find out what the moment is at the root. So the full length of the beam is A plus B. Okay, A plus B. So if we put the value of A plus B for the value of X into that equation, let's do that. Let's see what we get. Doing a different color here. So if X equals A plus B, which is the length of the beam, then the moment is going to be P into, well, you're going to have A plus B, and then you're going to have the minus A term there, aren't you? Okay, because this bit here is this bit here. So you can see that the A's cancel out, so you're going to have the moment is going to be equal to P times B. So that's just this constant term here. And then it's going to have to be a linear straight line. So it's going between those 2 points there, where this value here is P B. And this is the moment. So you can see how the bending moment varies over the beam. So that's for a cantilevered beam. I've done it in a generalized form. In the next video, I will put some numbers to that so that you can see how it works out with an actual physical example.